Welcome back, everybody, and welcome back to this lecture on quantum computing and quantum machine learning. And the topic the last weeks are going to rotate around quantum machine learning. And last week we went through the mathematical details of support vector machines, the classical ones, and their implementations. And we discussed also some of the basis for quantum support vector machines and what are the differences. We are going to revisit some of these arguments today. And we're also going to look at, after we've gone through that, we're going to look at how we encode data. And we are going to define what is called a parameterized quantum circuit, which at the end is what we end up doing. And we are going to look at specific implementations of quantum support vector machines. We are going to look at some selected data sets. We have one credit card data set in the lecture notes. And we also have the classical Iris data set, where we are going to analyze these data sets using both a classical support vector machine, as it is included in a standard library like scikit-learn, which is a widely popular library. And we are going to use PennyLane in order to encode the quantum kernels, which we discussed last week as well, and see how we can fare when it comes to the different calculations. So when we have built a quantum hardware, then the question is obviously how can we use it to the maximum effect, given its scale, connectivity, and fidelity rates, the fact that we can entangle qubits, the fact that we can look at superpositions, deal with quantum parallelism, and many, many other features which the quantum advantage offers us. So these questions are often best answered if we can split it into normally two parts. So one part is actually a problem which would be solvable on this NISQ era quantum computers. And secondly, the other topic is actually how do we encode classical information into quantum states. So one of the first topics we will talk a little bit about today, after we have reminded ourselves about some basic elements of support vector machines, is actually to look at how we encode the data. So we will mainly, in this course, we will mainly focus on what we call classical data in a supervised context. So as soon as we have decided that we need to actually look, before we get started, we need to look into the data encoding part. And that is actually a very important part and relies on several practical methods, which we are going to look at today. And this is actually, and I should say so, this is an active area of research where we can expect most of the progress to come from the quantum software side. Now, let's just quickly remind ourselves of some of the small technicalities which we discussed last week. So the idea of a classical support vector machine is that we have a set of points that in either one group or another, and we want to find a line that separates these two groups. So if we have just two features, a simple case, which we discussed last week, then a line is what would separate the two features ideally. But often we cannot separate them immediately. And then we would transform the data by this technique which we introduced last time, which is the technique of kernels. So when we think of a quantum support vector machine, one of the basic ingredients, and we will come back to this, is how we encode the classical data. We are going to look at examples. And then when we have encoded the data, we're actually going to set up a quantum circuit, which is normally called a parameterized quantum circuit. And we have already met examples of this when we looked at the variational quantum eigensolver, because that was also when we used the variational principle, it was an example of a parameterized quantum circuit in terms of various angles theta. And we are going to meet this again. You will see also a basic procedure like this one, where we rewrite this in terms of a parameterized circuit, which we optimize by taking the gradients of these parameters. So these algorithms are often a kind of hybrid algorithms in the sense that they contain a quantum mechanical part, which is the encoding of the data, and it's also the setup of the circuit. But then the optimization part of the parameters is something which is done via classical optimization algorithm, which we have met again and again. And many of you in the first project you used all the kinds of optimizers which are on the market, like Adam, root mean square propagation, or just plain gradient descent. And then finally, there's the measurement part. So mapping, the data encoding part is actually one of the things which we will discuss partly today. So the input data is first encoded into some quantum states. And this is similar to what we normally call, or it is actually what we would call a quantum feature map, where classical information is represented in the quantum Hilbert space. And this is something we will cover in the whiteboard notes. I also recommend you the textbook by Maria Schult and Francesco Petruccione, which is one of the textbooks we refer to in this course. And that textbook contains a detailed chapter, chapter 5, on different ways of encoding the data. And we are going to look at some of these examples and how we then would feed into what we call a parameterized quantum circuit. But let's remind ourselves about some of the things which we discussed last time and switch back to the whiteboard. So we need to remind ourselves about some of the technicalities which we went through last time. And one of the things which we discussed last time in connection with the support vector machines, so let's quickly remind ourselves of that, is that at the end, we ended up with a Lagrangian, which is the function we want to optimize, which is now given in terms of some unknown Lagrangian multipliers, lambda y's. And this runs over all the data points which we have. So if you would have something like 100 data entries, this n runs up to 100. And then we have, after we calculated the gradients of L with respect to the parameters lambda, we could then replace them and find an expression, which is the one we end up optimizing by standard libraries like convex optimization libraries, which exist with Python. So we've had now a double sum where we have the unknown parameters, and these parameters are constrained. I'm not going to repeat everything with the derivation of these equations. And the y's are the outputs of the model. So if this is a binary type of problem, the y's could be equal to -1 or +1. And then we have a kernel, which then represents the input data with the features. And I'm putting arrows on this to indicate that these are vectors. And the simplest type of kernel which we went through was a so-called linear kernel. And that was the example which we used in the first derivation of the equations for a support vector machine. Then this kernel as a function of kx and xj is something we would write like this. And in the linear case, this was just given by the inner product between these two vectors. But this can be actually made more complex. So we can have functions which transform the data, which often can be very useful if we want to separate the data clearly for the two different types of, let's say, type of outputs which we have. But we are not limited to only a binary type of problem. We can have a multi-class optimization problem. Now, one of the things which we did last time was just to define an intermediate variable, which we label as a y, as an h, which is a function of y of I and lambda of I. And then one of the standard assumptions which we make is that this equation here is actually an equation when we rewrite it like this times a kij. We assume that this is a semi-positive quantity. And for each set of n, then there is actually, if this is the case, then for each set of n, and we have these h of i's, which we assume to be real numbers, then there is a mapping which we label as a phi of x, such that this function k can be rewritten as kij, which is now the transpose of this function phi of x of I and phi of x of j. And we could then actually rewrite the previous equation as a sum of I equal 1 up to n, and then we have an h of I and phi of t of x of I multiplied with an x summation from j equal 1 up to n of h of j and phi of x of j. So this defines a so-called feature function. So this is normally often called a feature function or feature mapping. So these are often names which are used interchangeably. And if we have features which can be well separated by such a transformation, then we can be pretty confident that we will be able to develop an algorithm which can then allow us to separate the different outputs properly so that we can use this model to make predictions on data sets which were not included in the training. So you would often find this function, so this feature function mapping is often written as a function of x, where we now just look at one of the sums of h of I, and then multiply with k, and then we have phi of x of I of phi of x. And this function is something which we can make a quantum mechanical equivalent of. So typically what we ended up with then when we made a quantum mechanical equivalent, and we discussed some simple cases last time. So the quantum mechanical equivalent means that we translate our x of I over to a phi of x of I. And this mapping is something which we will discuss a little bit later when we are going to look at different ways by which we can encode the data. So we make a mapping from x of I to a quantum mechanical state, and then we assign the label y of I when we observe such a state. So what we are saying here, or what we are writing here with this mapping, is, just to repeat myself, is that we make a mapping from x of I to a quantum mechanical state, and then when we observe this specific quantum mechanical state, then we would assign a label y of I to the output when we make our measurement. Now, quantum mechanically, this quantity, if we now just remind ourselves of the density matrix of rho of x, and I'm just for plain laziness, I'm going to skip the vector signs. This is given by so this is the definition of the density operator, the density matrix. So this is the outer product between the two vectors. And we know that that is a matrix. And this object, which we defined classically, has a quantum mechanical counterpart. So this is our Kij. This is given in terms of the trace of the density matrix for the variable x of I with the density matrix of x of j, the trace of that one. And this turns out to be simply phi of x of I or phi of x of j squared. Now, one of the cases which we looked at last time was a data set which we now transformed. And I'm going to introduce this model again. It's a pretty simple model. So if we start with the basis set 0, which we have seen many, many times now, 1, 0, and 1, which is 0, 1 here. When we now make this parameterized quantum state, what we typically end up with, so we have a parameterized state, which is going to lead to a parameterized quantum circuit, which is the one we will optimize at the end for a specific algorithm. We would typically introduce a rotation matrix around an angle x, which is given as e to the minus I of x. So this is along the x direction. So that means that we have the Pauli X matrix. And just to quickly remind you, the Pauli X matrix is given by 0, 1, 1, 0. And we know that this R of x, when we now use the properties of the exponential, we just expand the exponentials. This is given by cosine of x half multiplied with the identity matrix minus I times sine of x half multiplied with the Pauli X matrix. And then what we are going to do is what we did when we looked at the variational quantum eigensolver. We are going to introduce a parameterization in terms of this angle x, and we are going to act on an initial state. So we are performing a unitary transformation on an initial state. We would prepare our system, which now in this particular case is just a 1-qubit system. We would prepare a 1-qubit system by performing a rotation. And this is something which we have done many, many times. And this gives us our phi of x. And then with that one, we can then calculate the density matrix, which in that case is just simply phi of x. And as I said, I'm a little bit sloppy now. I'm skipping the vector signs on the x's. And what we found then is that this specific kernel, which we define for that case, is given by k of x. And if we take an x prime here, if we now just introduce the vector signs, this is something which is going to be given by a cosine for this specific case of an x minus x prime. We don't need the vector signs here because we are not, these are just angles now. And this is cosine divided by 2 n squared. So the density matrix is then going to be given by some terms which are proportional to this one. And for that specific type of preparation of initial state, this is actually what we will end up with. Now, when we are going to set up now the calculations for a support vector machines in a quantum mechanical way, what we need to keep in mind now is a distinction between the classical way we encode things and the quantum mechanical way we are going to encode things. So let's just quickly remind ourselves about this kind of more overarching pictures. So if we look at the data encoding, which is going to be one of our first steps here. So if we look at this from a classical point of view, what we will have then is the data which we are going to feed in. So this is our data set. And typically we have some input x. And then this is now fed into the machine learning algorithm. So one thing which we haven't discussed much is actually how we prepare the data properly. And this involves typically us scaling the data in one way or the other one. A typical situation is to scale it to a specific domain, or we can also subtract the mean value in order to avoid a dependence on outliers when we're going to make the fit. So there are many ways to prepare the data so they are as best fit as possible for a specific machine learning algorithm. So in here, we would then have a machine learning algorithm where we perform the training, we find the optimal parameters, and when we are done then, we would make our predictions. And this prediction is something which we would typically label with a y tilde. And these predictions enter then a function, or it's a cost function, which now depend on our predictions and the data sets which we want to reproduce. So this is the classical algorithm for a machine learning process. When we now do the quantum mechanical aspect of this same algorithm, we would then start again with a data set. So let's now look at the quantum mechanical. quantum mech. So we would still now have the data set, which we are going to view as a classical data set. So in our course, we will not deal with data which are generated by a quantum mechanical algorithm. So this classical data set could be us looking at some credit card data in order to be able to predict whether a specific customer will respect the credit card debt or will default on the credit card debt. So we have the data set with the x's, the inputs, and the outputs y's. Now, this is now transferred. When we now look at the quantum mechanical part, there needs to be an encoding part. So this is where we now need to transform the classical data into a quantum mechanical representation. And there are several ways by which we can do that. And we will be discussing that pretty soon now. Then what we will have next is what we call a quantum mechanical algorithm. So we're going to use the acronym QML. Then when we use this algorithm, there's a readout part. And this is where we perform the measurement. And when we then have done the readout, when we associate to this specific data set a specific output, that is when we make the predictions. So let's just mark some of these things. So this is actually a quantum system state preparation. So we need to initialize the qubits which we have available in a specific format. Then when we have the quantum algorithm, here we would typically have some parameterized quantum circuit. And this involves typically unitary transformations. It's a series of unitary transforms. Then finally, the readout part here is actually a measurement. So if we think back to the variational quantum eigensolver, this is actually not that different from what we are going to do here. So we would typically convert this into a specific basis or computational basis, and that means transforming the XYZ Pauli matrices into some specific basis, which is an eigenbasis of one of these matrices, and then we perform the measurement. And that measurement leads to the predictions, which we then compare with the output, which we would typically have at our hand. Now, if we now look at the problem from another point of view, if we think a little bit, I mean, what we are going to deal with is something which is called a parameterized quantum circuit. QC stands for quantum circuit, and they are trained using some hybrid quantum classical protocols. So as I said, I mean, the typical update of the gradients is normally done by us running a standard gradient descent algorithm with some ways to update the learning rates. But what we would then have is a rough scheme which can look like this. So we would have now a user here. And in this specific case, this protocol which we are setting up now, we would have some problem which we want to solve. Problem model. So we define a problem, we are setting up a model, and then we have input and training data, and input / training data. So if you look at the kind of protocol here, as I said, this is going to be a mix of a classical computational part and a quantum mechanical part. So there is a classical component where we have the initial data, initial data with some pre-processing of the data. So the pre-processing could be us normalizing the data to a specific domain. For instance, we can, if the data have a big scatter, we could normalize them to a domain which runs from 0 to 10 or 0 to 1. We could scale the data so that we subtract the mean value for each feature in order to avoid possible dependence on outliers in the setup of a specific algorithm. Then this contains now a post-processing. And then we have a parameter. So let's now, if we now look at what's done here, this moves over to the quantum mechanical part when we now have done the classical initialization of the data. So in here, we would now set up a parameterized quantum circuit with different parameters. And then we would be running the quantum circuit with the parameters which we have initialized it with. This includes also state preparation. So we need to initialize the quantum computer in a specific state. So this could be us, if we have 10 qubits, we could set all the qubits to be 0. And then we have the measurement part. So these were the 3 steps which we discussed on the previous page. Then this is fed back. So we perform a measurement. This is our result from the quantum, running the quantum computer. So up here, we should call this the quantum computer. So it's pretty close to what we did with the variational quantum eigensolver. And when we have this is fed back. And then we have the post-processing part. And we have the parameters update. Which essentially often means just us updating the gradients. And this goes back and forth. So when we've updated the parameters, then these are then fed back into the quantum computer. We run the quantum circuit. We have already performed the state preparation. And then we perform a new measurement. This is fed back. We have new parameters, which we would update with a standard gradient descent. So this is a kind of a classical quantum hybrid algorithm where we would have a specific part which now deals with the quantum circuit, the state preparation, and the measurements. And then we would then have the, after the measurement, we have a specific result, and this is fed in here. We update the parameters and then go back and forth till eventually these gradients do not change by more than a quantity which is set by us in an iterative fashion. So let us now look at a smaller example and a case which allows us to understand a little bit better what is going on. Could be the following. Suppose we have the 4 possible classes. Just to show you how we could do the encoding. This is just a simple example. And we could label these classes like 0, 1, 2, and 3. And then what we could do when we do the quantum mechanical encoding, we could think of this being encoded in terms of a system with 2 qubits only. So that means that we would have states, which we earlier have labeled as 0, 0, which is just the tensor product between a qubit 0 and a qubit 0. And that means that we could set up a bit string, which now corresponds to this 0, 0 state. Alternatively, we have the 0, 1, which we know is the tensor product of 0 and 1 here. So that would obviously be the 0, 1, and then it's pretty obvious to see that this continues with the 1, 0 and 1, 1. And then when we make the measurements, you could now think of having a set of measurements. So this would be the ways which we would encode the classical information. And then we could perform a set of measurements. And this is actually what we are going to see when we run a code. And you could think now that if we run something like 1,000 shots, so we rerun the experiment 1,000 times, you could then think of this giving us 100 measurements. So these are just numbers which I'm making up. This could be 550 measurements. This could be 200 measurements. And this could be 150 measurements. Then what we can conclude in that specific case is that the most likely label class for the given input is this class 1, which we have here, because this is the one which has the largest number of measurements. And this is something which you will see when we are now setting up the type of measurements we're ending up with. We are going to set up a histogram over all the possible measurements. Okay, so let's now switch over to the typical types of encoding, which you will encounter in many of these applications here. So when we now have decided on how to perform the encoding, one of the standard ways by which we would typically now encode information is by using a representation of a qubit on the block sphere. So that means for us that a given state psi will now be given by, if we are now thinking of just one qubit, so there's going to be an angle theta half, and then we would have an e to the I of phi multiplied with a sine of theta half. This is a typical encoding of a random state on the block sphere. And we know that theta is an angle which now lives between 0 and pi. And phi is now an angle between 0 and 2 pi. And they uniquely define the position of the qubit on the unit sphere. And since we need two continuous variables to specify the qubit state, a single qubit can actually encode two real-valued features. Now, we can illustrate this with a kind of basic encoding scheme by thinking of a set which has 8 features. So suppose now that we have as an example an 8-feature data set. So the feature of a data set could be, if you're looking at an example like housing prices, it could be, one feature could be the number of bathrooms you have. The other feature could be the number of rooms you have. Another feature could be the size of the house, the number of floors of the house, etc. So suppose now that you just have such an 8-feature data set with a given number of samples. So this could be the number of houses. So these are the features which uniquely define the houses which are putting on the market. So this has n samples. And all these features are real valued, and they have some extremal values. So what we could set up then, so we have all x1 to x8 features are real valued. And the extremal values, so if we now let I be given from 1, 2, up to 8, so these are the number of features which we have, then there is an xi min and an xi max. And these are quantities which we can compute, and this would typically be done by the classical quantum computer. So for every sample which we have, so for every sample, where we now have j runs from 1, 2, up to n, the number of samples. This would be the number of houses. If we're now insisting on this housing data set, then we can establish a one-to-one mapping between the value of a given feature and the corresponding rotation angle. So we can establish, so keep in mind now that the subscript I stands for the features and the subscript j stands for the samples. So we can establish a one-to-one correspondence, a one-to-one correspondence between rotation angles. So we can have a rotation angle theta ij, and this is given by some x ij minus x. So this is a kind of scaling which we're also doing, and xi min divided by some xi max minus xi min and multiplied with pi. So where the xi min is actually the minimum value in the data set xij. So when we say this xi min, that is actually the minimum. And this is where we would typically minimum with respect to j of xij. And similarly, xi max has to be the maximum with respect to j and of the variable xij. So that means that the rotation angles, they then generalize the angles theta and phi in the standard block sphere representation of a given state. So if we now have two angles per feature which we have, we could now actually let each angle represent the features. So that means that we could now have a initial state 0, and that is now encoding one of the features, and we could think of this as a rotation along the y-axis with an angle theta 1. And then we have the next qubit, which then has a new angle theta 2. And then we have now a new rotation here along the y-axis again of theta 3. So we have 8 features, and we can encode these 8 features in these 8 angles. And you will see in the codes which are coming here that this is a kind of angle embedding, as it is called, is something which we then typically use in order to transform the classical data into quantum mechanical data. So we need to do that in order to be able to let a specific qubit represent some kind of information which we are feeding in. And then we could perform a rotation around an angle 5 along the z-axis. We would now have a new angle, or z of 6. And then we would have a new rotation, rc of theta 7. And finally, we have an rc of theta 8 here. So this is a typical way by where we would have a 4-qubit quantum circuit for an 8-feature sample encoding. So this is one of the ways by which we can do that, and that means that we can have a mapping of classical data into a quantum state. And that simply means that what we could have then is that this data set x of j is now encoded into, so we would have this x of j. If we now look at that one, that is something which we would write as an x of j feature 1, x of j feature 2, and all the way up to the 8 features which we have. And these are all real numbers. And j runs from 1, 2, up to n, the number of samples which we have. So these xj's could then be encoded in terms of tensor product, because if we go back to the image which we have here, then all these states would then be encoded at the end as a tensor product here. So we perform the individual rotations, so these are single qubit operations acting on each qubit, but the final state is a tensor product of all these states. So that means that when we are setting this up, we need to indicate that this I equal 1 up to k here, where k now represents all the possible data which we have. This is now given in terms of a cosine, and then we have these angles theta ij divided by 2, acting on 0, plus I, or sine, of theta ij, 2, acting on 1, and finally, sorry. So this is a way by which we could now encode the information. Another way by which we can encode this information is to actually look at something which we would call for an amplitude or a basis encoding. So let's look at another way of doing this. And this goes back to the first case which we had. So basis encoding is also something which is widely used. So if we now have a binary data set where we have a set of strings, so we could now assume so that we have a binary data set. This is particularly useful if we have a binary data set, which we just label as D, where each pattern of data points which we have, X of M, and M is one of the data sets which we have, is element in D, is a binary string. So that means that we have some X of M equal to some B1 of M, and this goes all the way up to some Bn of M. And each of these, Bi of M, they take only binary values. So they could typically take values -1, 0, 0, 1, etc. So these are just the binary values. What we can do then is we can prepare a superposition of basis states so that where each qubit then corresponds to a binary input patterns. So suppose now that we have a specific state, an input x1, which now contains an input like 0, 0 and 0, 1. And then we have another one, which is just 1, 1 and 1, 0. So in that specific case, what we could think of is that when we now write them in a binary pattern, if we take these data sets, then this x1 could be written as a binary word like 0, 0, 0, 1. And this x2 could now be written out as a 1, 1, 1, 0. Now we could then think of this being represented by some quantum mechanical basis states. So, and we would then represent, and in terms of basis states. And you see quickly now that these are basis states which would involve 4 qubits. So that means we could have the basis state 0, 0, 1 and the basis state 1, 1, 0. So that means that we would then have a superposition of these two states. So that superposition of these two states is then a state, which we just label as psi here, which would then be given by 1 over square root of 2. And then we would have the state 0, 0, 0, 1, plus a state which runs like 1, 1, 0. So that's another way of thinking of representing this state. And clearly, what we end up doing after we've done that, going back to this angle representation, if we have different features, we will then typically perform these transformations in order to embed everything into what is going to be called a parametrized quantum circuit. So in this specific case, we need 4 qubits. So we have 2 to the power of 4, and that means that 16. And we need 4 qubits to represent these combinations. And then we would have, in final, we would have 16 basis states. And if you now think of this basis state 001, this could be a state which is now the tensor product of these combinations, 1, 0, 1, 0, and finally with 0, 1 here. If we then go back to what we did earlier, you may remember that in connection with the quantum Fourier transform, we rewrote a given state. So the state which we had previously, we could write it in terms of, so these are 4 qubits. And we could have a qubit x0, x1, x2, x3. And the way we organize these qubits also becomes important. So this means that we could now set this x equal to x0 plus 2 times x1 plus 4 times x2 plus 8 times x3. And we see now that if x0 is 0 and x1 is equal to 0, x2 is equal to 0, and x3 is equal to 1, then that would correspond to a state which would have a label 8 in this system. So that means that x would now be in this specific labeling which we have, that would be state number 8. If I, on the other hand, take x in this basis equal to 1, 0, 0, 0, that would actually be state 1 in this labeling. So this is state 1. So this is state 8. If I take the other combination which I had with x in the base of 4, which is equal to 1, 1, 1, 0, if I now plug in the numbers here, this gives me simply that x equal to 7. So that is state number 7. And then I can continue this in this way and label all the possible states. So that means that when I'm now setting up the amplitudes, because the final state then can be written out as a linear combination of 1 divided by d, which is the dimensionality of the system, which in our case is 2 to the power of 4. So we have 16 states. So this is what we would call for d, the dimensionality of the system. So this would run from 1 up to d, and then we would have some amplitude alpha of I, and then we have this state x of I in the base of 4. So for that specific system which we looked at here, the one which had this combination as state number 8 and state number 7, which then corresponds to what we had here, we would actually need to correct this amplitude when we now are setting up the amplitude, because in that specific case, these amplitude vectors would then be given. So these amplitudes, which you see here, these alphas, this alpha of t would, for that specific combination we would have 0, 0, 0. So this is 1, 2, 3, 4, 5, 6. And then we have 1 over square root of 2, which is the amplitude. 1 over square root of 2, if we're looking at that specific state we put up. And then the remaining ones would be 0 up to state number 16. Or 15 actually, because the states will be labeled with that algorithm which we have as 2 to the power of 4 minus 1. So we start labeling with state number 0. So this is another way by which we can encode the information in this qubit system. And this is normally called a basis encoding, and it's pretty useful if we have a kind of binary set of encoding. The other one, which is pretty common as a way to encode information, is by this angle transformation, which we discussed here. And that means simply that we use the properties of the Bloch sphere by which we represent a given state here. So in the algorithms which you will see in the coming, we will use, for instance, this angle embedding, and we are going to show how you can actually set this up using a software like PennyLane. Now, there are other ways by which we can encode this. One is called Hamiltonian encoding, we've been going through amplitude encoding and also from for the binary case and with the angle encoding. And these are ways which we will see now these are ways to encode information, which we are going to see in the data set which we have.